Hello everyone. In this lecture, we're talking about heat stress equations, particularly those heat stress equations that you need to know if you are pursuing the CIH exam. The lecture, however, would contain some general information about temperature, heat strain, and other important concepts that the general health and safety practitioner should be aware of. At the end of this lecture, you should be able to define terms such as temperature, heat stress, heat strain, heat. You should also be able to describe physiological responses to excessive heat strain, explain what is a heat stress index. You should also be able to understand how to apply the heat stress equations found on the formula sheet for ABIHs Certified Industrial Hygienist exam. The first question we'll ask is, what is temperature? Now, there are several different definitions of temperature as it relates to different types of fields or subject matter. In thermodynamics, temperature is defined as a measure of the average kinetic energy of the microscopic particles in a system. The physiological definition, however, defines temperature as a measure of the heat energy present in a living body. The average temperature of a human body is 37 degrees Celsius. A very important temperature to take note of, as it will become very important in later parts of this session. The third definition of temperature is simply a measure of the degree of hotness or coolness of a body. Heat. What is heat? Heat or heating is a flow or transfer of energy from a region of higher temperature to a region of lower temperature. The pathway can be direct, as in conduction and radiation, or indirect, as in convection. But heat stress could arise out of several factors. One could be the clothing that is being worn. Thicker clothing has the ability to trap more heat and therefore subject the body to greater amounts of heat stress. The heat stress may also come from the external environment, or rather, the external environment can contribute to the net heat load that the body is subjected to. Under the external environment, that heat can come from radiant heat. It can also come from air movement. When the air is moving faster, it tends to take away a lot more heat from the body than if the air is not moving as fast. Humidity also plays a very important role in the heat stress that the body is subjected to. In its simplest terms, humidity is a measure of the water content of the air. When the air contains a lot of water, it makes it a little bit more difficult for sweat to evaporate off the surface of your body, and if sweat does not evaporate off the surface of your body, then the cooling effect is lost. So the higher the humidity, the more difficult it is for sweat to evaporate off of your skin, and the higher the net heat load would be as a result of the inability of the body to cool down as well as it would have if that sweat were to evaporate off the surface of your skin. The last factor in the external environment, of course, would be the air temperature itself. The higher the temperature, the greater the net heat load on the body. Heat stress can also be a result of the internal environment, or what you call metabolic heat. Metabolic heat comes from, of course, metabolism. Metabolism is the total sum of all the chemical reactions taking place in your body. So when you are running a little bit more, there's a lot more chemical reactions taking place, and there can be a lot more heat being generated. So in summary, the heat stress that a worker can be subjected to can come from the clothing itself trapping heat. It can also come from the external environment. and it may also come from the internal environment. Heat stress can lead to heat strain. Heat strain is a net physiological response to heat stress. So heat stress is the amount of heat the body is being subjected to, and heat strain is how the body responds to this amount of heat that it is being subjected to. The body responds to heat stress because it's important that the body maintains a very stable internal environment. We call that principle homeostasis. So when the environment becomes very hot, the body is going to try to do things to cool itself back down. So what the body can do, one we have here is vasodilate. Vasodilation is where the blood vessels expand. The point of that is to increase the flow of blood at the surface of the skin. This allows the blood to cool down a lot faster. Additionally, the body can also sweat. Sweating by itself does not cool down the body. It is only when that sweat evaporates off the surface of the skin is where you really have that cooling effect. Additionally, the body can increase the heart rate. Your heart pumps a little bit faster. There are a lot of other physiological responses that we didn't mention here, such as the hair on your skin would fall flat when you are subjected to a very hot environment. What this does is it traps less air around the surface of your skin, allowing you to be cooled down a lot faster. One or a few factors is not enough to appropriately determine the heat stress experienced by a worker. Example, if the temperature of the environment is comfortable to the 2 degrees Celsius, the heat stress can still be significant if the humidity is high and the worker is wearing layers of clothing. What this really means is one factor alone cannot determine the heat stress that you are being subjected to. The temperature alone of the atmosphere is not enough to represent the total heat stress that you are being subjected to. For example, 32 degrees Celsius in an environment with a very high humidity will not be the same as that exact same temperature of 32 degrees Celsius in an environment with a lower humidity. So what we would have done is create something called a heat stress index. A heat stress index is a single number which integrates the effects of the different elements that contribute to heat stress. This single number is expected to appropriately reflect the thermal strain experienced by the worker. The index value can be used to determine the effectiveness of hazard control. The wet bulb globe temperature was originally developed by the US Navy to assess heat stress. The index combined 4 main thermal components affecting heat stress: air temperature, humidity, air velocity, and radiation, as measured by the dry bulb temperature, natural wet bulb, and globe temperatures. The dry bulb temperature is the temperature of air not affected by humidity. The natural wet bulb temperature is the temperature measured when the thermometer is covered with a wick and exposed only to naturally occurring air movements. And the globe temperature is a measure of radiant heat. In the CIH, there are 3 very important equations that you need to know. 2 involve the wet bulb globe temperature, and the last one involves the heat balance equation. In this example, we are going to calculate the wet bulb globe temperature. So worker fainted while carrying out repairs on a boiler in the basement of a building. An industrial hygienist measured the following temperatures in the basement: What is the wet bulb globe temperature? So in this particular example, we use this equation. Notice we did not include the globe temperature. The globe temperature was missing because the worker is in a basement. Therefore, we are not expecting radiant heat. There is no sunshine shining directly on that worker. So when you plug in your values, you are going to get your final answer of 34 degrees Fahrenheit. Let's look at the heat balance equation. S is equal to the change in body heat content, M minus W equal to total metabolism minus external work performed, C equal convective heat exchange, R equal radiative heat exchange, and E equal evaporative heat loss. If you examine this equation, you realize that it contains all the important factors that can contribute to the heat gain or loss by a worker or by any other human. Convective heat exchange refers to the heat that is either gained or lost from the flow of air around the worker. Radiative heat exchange refers to the heat radiated either away from the worker or heat absorbed by the worker via radiation or electromagnetic waves. E equal evaporative heat loss. If you notice this particular equation, there's only negative E, meaning that you can only lose heat by evaporation. The C is actually something that you have to calculate. The C, or the convective heat exchange, in BTU per hour, you can calculate it using this particular formula, where VA is equal to the air velocity in feet per minute, TA equal ambient air temperature, and TSK equal the mean weighted skin temperature, usually assumed to be 35 degrees Celsius or 95 degrees Fahrenheit. It is very important for the exam that you keep the correct units. If you mix up your units, you are going to end up with a wrong answer. To calculate the R, we use this particular formula. Now, these formulas are not on the formula sheet, so it's something that you need to know beforehand if you want to successfully apply that heat balance equation. R is equal to the radiant heat exchange. The TW is the mean radiant temperature, and the TSK is the mean weighted skin temperature. And the E, of course, that's evaporative heat loss, is given by this particular equation, where VA equal air velocity, PA equal water vapor pressure, and PSK equal water vapor pressure on the skin, which is assumed to be 42 millimeters of mercury at 95 degrees Fahrenheit or 35 degrees Celsius. Thank you guys for being part of this session. Please subscribe to the channel so you can grow and we can develop a community here, and we look forward to you participating in future sessions.